In this tutorial we will cover chapter 7, which is Discrete Probability. Of course, probability, when you discuss probability you can talk about continuous probability theory or discrete probability. We are interested in discussing discrete probability, and we will use some of the ideas we learned from counting can be used to calculate probabilities. The sections that we will cover are the following: Introduction to Discrete Probability, Probabilities of Complements and Unions of Events, Probabilistic Reasoning, Assigning Probabilities, Probabilities of Complements and Unions of Events, Conditional Probability, Independence, Bernoulli trials and the binomial distribution. The last three topics will not be covered in this course. Bayes' theorem is optional material. You can read it if you're interested, but it's not included in the course. We will start by looking at some definitions that we will be using when we study discrete probabilities. First of all, an experiment is a procedure that yields one of a given set of possible outcomes. The sample space of the experiment is the set of possible outcomes, all the possible outcomes. And an event is any subset of the sample space. Here is an example of an experiment, and we will see what the sample space is and examples of an event. The experiment of rolling one die. Of course, the die is a cube that has 6 sides with numbers 1 through 6 on each of the sides of the cube. When you roll one die, the possible outcomes which define the sample space. The sample space in this case, you can get 1 or 2 or 3 or 4 or 5 or 6. This is the sample space, the set of all possible outcomes. An example of an event, E1 equal 1. Any subset of the sample space is considered to be an event. E1 here is just a set that has the number 1, is an event. It's a simple event because there's only one outcome. This event occurs if we roll the die and get 1. That's the event, the event of getting 1 when we roll a die. Again, this is called a simple event because there's only one outcome in that event. Another example of an event is 2, 4, or 6. This is a compound event because there's 3 possible outcomes. This outcome is satisfied if we get either 2 or 4 or 6. Or you can think of it as the event of getting an even number. Of course, the sample space depends on what we're interested in. For the same experiment, if we're interested only in whether the outcome is even or odd, there's only 2 possible outcomes. Either the number is even, if we get 2, 4, or 6, or the number is odd, if you get 1 or 3 or 5. There's only, if we're interested only in whether the number is even or odd, there's only 2 outcomes. The sample space has 2 outcomes, even or odd. Next, we would like to see how we can assign probability to any outcome or any event. So we will start with set S. S is a finite sample space of equally likely outcomes. So we have an experiment and S is the sample space. It is the set of all possible outcomes. Now, when we say that the events are equally likely to occur, that means every outcome has the same chance of occurring. So how do we calculate the probability of an event? The probability of an event is defined in this case to be the number of outcomes in the event divided by the total number of outcomes, the number of outcomes in the sample space. So from the definition, it should be clear that the probability of any event is a number that's larger than or equal to 0 and less than or equal to 1. Because, of course, the probability is the number of events in the subset divided by the total number of elements in the set, so it will always be less than or equal to 1 and greater than or equal to 0. Let's look at an example. We have a coin is tossed twice. What is the probability that at least one head occurs? The first step, of course, before we calculate probability is to decide what the sample space is. The coin is tossed twice, where the possible outcomes are head-head, meaning a head in the first toss and a head in the second toss, or head-tail, meaning a head in the first toss, a tail in the second toss, or tail-head, meaning a tail in the first toss, a head in the second toss, or tail-tail, meaning we get a tail in both tosses. These are all the possible outcomes when you toss a coin twice. Now we want to calculate the probability at least one head occurs, so we have to decide what that event is. To get at least one head, there's 3 outcomes that satisfy this condition: head-head, head-tail, or tail-head. And the probability of each outcome in the sample space is equally likely. The probability of E would be the sum of the probabilities. Each one of them is 1 over 4, so the probability of getting at least one head is 3 divided by 4. Let's look at more examples of calculating probabilities. Suppose we have an urn that contains 4 blue balls and 5 red balls. We want to know the probability that a ball chosen from the urn is blue. Since there is a total of 9 balls in the urn, and each ball is equally likely to be drawn, the sample space has 9 outcomes. 4 of these balls are blue, so the probability of selecting a blue ball will be 4 divided by 9. Next example, we want to know the probability when 2 dice are rolled, the sum of the numbers on the 2 dice is 7. First of all, we want to know what the sample space is. You have 2 dice. Each dice has 6 possible outcomes, so the 2 dice together, there's 36 possible outcomes. The sample space has 36 possible outcomes. Now 6 of these sums add up to 7. If you take 1 and 6, or 6 and 1, 2 and 5, or 5 and 2, 3 and 4, or 4 and 3, these all add up to 7. 6 possible outcomes will add up to 7. But the probability of obtaining a total of 7 is equal to 6 over 36, because we have 6 outcomes that produce a sum of 7, 6 divided by 36, or you can simplify it, it is equal to 1 over 6. Here is another example of calculating probability. In a lottery, a player wins a large prize when they pick 4 digits that match in correct order. 4 digits are selected by a random mechanical process. What is the probability that a player wins the prize? First of all, we have 4 digits that must be selected. How many ways can you select 4 digits? Well, there's 10 choices for each digit from 0 to 9. where the number of ways to select 4 digits is 10 times 10 times 10 times 10, which is 10,000. Now there's only one way to pick the correct digits, the correct order, where the probability of winning the large prize is 1 divided by 10,000, or 0.0001. There is a smaller prize that the player can win if only 3 of the digits are matched. What is the probability that a player wins the smaller prize? Well, if exactly 3 digits are matched, that means one of the digits must be incorrect. The other 3 digits must be correct. Now, for the digits that's incorrect, there's 9 possible choices, because, of course, there's 10 numbers. One of them is correct, so there is 9 ways to select the wrong digits. And now the wrong digits can occur in the first digits, or second, or third, or fourth. So the number of ways of selecting exactly one incorrect digit is 9 plus 9 plus 9 plus 9, or 36 possible ways to choose 4 digits in a way that exactly 3 of the digits is correct and 1 digit is incorrect. Where the probability of winning the small prize is 36 divided by 10,000, or 0.0036. We have another example that deals with lotteries. There are many lotteries that award a prize to people who correctly choose a set of 6 numbers out of the first n possible integers, where n is usually a number between 30 and 60. We want to know what is the probability that a person picks the correct 6 numbers out of 40. But here the number of ways to choose 6 numbers out of the 40 is C, this is the number of combinations, 6 combinations out of 40. The number of ways of selecting 6 out of 40. This is 40 factorial divided by 34 factorial times 6 factorial, or equal 3,838,380. The probability of picking the winning combination is 1 divided by that number. This is a very small probability, 0.00000026. Let's look at more examples. What is the probability that the numbers 11, 4, 17, 39, and 23 are drawn in that order from a bin with 50 balls labeled with the numbers 1, 2 through 50. We want to calculate the probability under 2 different conditions. A, if the ball selected is not returned to the bin. This is called selecting or sampling without replacement. And also we would like to calculate the probability if the ball selected is returned to the bin before the next ball is selected. This is sampling with replacement. In the first case, if the ball is not returned, we want to count the number of ways of selecting 5 balls. There's 50 different ways to select the first ball. Since there is no replacement, there's only 49 ways to select the second ball, 47 for the third ball, 46 for the fourth ball, and 45 for the fifth ball. So the product of these numbers is 254,251,200 ways to choose 5 balls. And of course, there's only one way to select these in the correct order, where the probability will be 1 divided by 254,251,200. To solve the other problem, sampling with replacement, that means we return the ball before we select the next ball. Well, in this case, the number of ways to select the 5 balls is 50 multiplied by itself 5 times, or 50 raised to the power 5. Where the probability in this case is 1 divided by 50 raised to the power 5, or 1 divided by 312,500,000. Now we would like to talk about the probability of complements. احنا طبعا we discussed what we mean by the complement of a set. Remember now, an event is just a subset of the sample space, so we can talk about the complement of an event, and we will see طبعا also how to calculate the union of events, يعني the probability of the union of events. First, we would like to define what we mean by the complement of an event. Let E be an event in the sample space S. The event E bar is just the complement of E in the sample space. Yani, as a set of S, the complement of the event E is the complement of E as a subset of S. So it's the set of all events in the sample space that are not in E. Here we can calculate, this is called the complementary event of E, or the complement of E. The way to calculate the probability of the complement, probability of the complement of E is equal to 1 minus the probability of E. Now, to calculate the probability of the union of events, the probability of E1 union E2 is equal to the probability of E1 plus the probability of E2 minus the probability of the intersection of E1 and E2. And that, of course, again, this follows from the fact, and the way to calculate probability, we are counting the number of events. This is based on the counting rules for the union of two sets. It follows that the probability of the union of events is calculated by adding the probability of the two events and subtract the probability of the intersection. Of course, if the two events are disjoint, if they don't have anything in common, then the probability of the union of the two events is just the sum of the two events, so the sum of the probability of the two events. Let's see how we can apply this rule, the relationship between the probability of an event and its complement, is a useful formula to calculate the probability in some cases. Let's do an example that uses that formula. We have a sequence of 10 bits is chosen randomly. What is the probability that at least one of these bits is 0? We will let E be the event that at least one of the 10 bits is 0. What is the complement? The complement now will be the event that all of the bits are 1s. None of the bits is 0, for all the bits are 1, and there is only actually one bit string that has all 1s. Now, what about the sample space? How many possible bit strings of length 10? This is just 2 to the 10. For the probability of E, the probability, we get at least one bit that's equal to 0, is 1 minus the probability of the complement, which is 1 minus the number of elements in the complement. There's only one bit string that's all 1s. This is just 1 divided by 2 to the 10. The probability of getting at least one 0 is just equal to 1 minus 1 divided by 2 to the 10, which is 1024. The final calculation is 1023 divided by 1024. Next example, what is the probability that a positive integer selected at random from the set of positive integers not exceeding 100 is divisible by either 2 or 5? يعني when you think of this event, when you have يعني you want to know all the integers that are either divisible by 2 or 5. Anytime you see or, that's the union of two events. We would like to define E1 to be the event that the integer is divisible by 2. E2 is the event that the integer is divisible by 5. What we are interested in is just the union of the two events. We want to know the probability that you get a number that's divisible by by 2, which means it's from E1, or divisible by 5, which means it belongs to E2. This is a union, E1 union E2. Now we have to also consider the intersection. E1 intersected with E2 is the set of integers divided by both 2 and 5. The probability of E1 union E2 is equal to the probability of E1 plus the probability of E2 minus the probability of the intersection. The probability of E1, there is 50 integers divisible by 2, so the probability is 50 over 100. The probability of E2 is 20 over 100 because there's 20 integers divisible by 5. Minus 10 over 100 because there's 10 integers that are divisible by both 2 and 5, and divisible by 10. Then the probability will equal, and if you do the calculation, you should get 3 divided by 5. Now the Laplace definition assumes that all outcomes are equally likely. Now there is some experiments where the outcomes are not equally likely. We will see how to solve problems in the case where the outcomes are not equally likely. But there are some things that we should agree on, and for probabilities there's two conditions that are always true. Anytime you have a sample space, S is a sample space of an experiment with a finite number of outcomes, the probability, any definition for probability, the way to define the probability of any event must satisfy those two conditions. The probability of any outcome or any event in the sample space must be greater than or equal to 0 and less than or equal to 1. Whichever way you assign probability, the probability must always be less than or equal to 1 and greater than or equal to 0. The second condition that any definition of probability must satisfy is that the sum of the probabilities of all the outcomes in the sample space must equal to 1. Now anytime you have a function that assigns probability, then you can define actually a function for each outcome in the sample space. A function can assign a probability for that outcome. This function starts from the set of all outcomes. The domain here is a sample space. This is called the probability distribution. We will look at examples of probability distributions, and at least now we know in any assignment of probability must satisfy these two conditions. Now let's look at more examples. What probabilities should we assign to outcomes? And then tossing a coin, there's two outcomes, heads or tails. We want to know how to assign probabilities for heads and tails when a fair coin is flipped. That's one case. And then we would like also to see how we can assign probability in the case where a coin is not a fair coin. A fair coin, that means the probability of heads is equal to the probability of tail. If the coin is not fair, then we call it biased. That means one outcome is more likely to occur. We want to calculate it in the case where you have a biased coin, such that heads comes up twice as often as tails. The first case, when you have a fair coin, you have equal probability. The probability of heads equal to the probability of tail equal to 1/2. That is in the case where you have a biased, fair coin. Now for a biased coin, where the probability of tail, the probability of head is twice as likely as the probability of tail, it must satisfy the condition probability of heads equal to 2 probability of tail. But we do know that the sum of the two probabilities must equal to 1. For 2 times the probability of tail plus the probability of tail, which is 3 times the probability of tail, is equal to 1. That means the probability of tail must be 1/3. The probability of heads is twice as much, so it should be 2/3. And you still have the condition that the sum of the two probabilities is equal to 1, and the probability of heads is twice as of the probability of tail. Here is examples of distributions, probability distributions, starting with the uniform distribution. Suppose S is a set with n elements. For the uniform distribution, assigns the probability of 1/n to each element of S. We think of S as a sample space that has n possible outcomes. The uniform distribution assigns equal probabilities. It's simply 1/n for each element of S. But this is the same, of course, as our original definition of function in the case of equally likely outcomes. Let's consider again the coin flipping example. A fair coin is an example of a uniform distribution. The probability of head equal the probability of tail equal to 1/2. Another thing we should think about, and especially if the probabilities of different outcomes are not the same, the probability of an event is the sum of the probabilities of the outcomes in E. The probability of any event E is the sum of the probabilities of the different outcomes in E. Now, there is no assumption made here about the distribution. It doesn't matter whether the outcomes are equally likely or not. It should always be the case that the probability of an event is the sum of the probabilities of the different outcomes in the event. Okay, let's do some examples. Suppose that a die is biased. Again, a die is biased. That means one of the outcomes is more likely to occur than the others. Let's assume we have a die that is biased so that the number 3 appears twice as often as each other number. But the other 5 outcomes are equally likely. The other outcomes are 1, 2, 4, 5, and 6. Then the other outcomes are equally likely, but the number 3 is twice as likely to occur. What is the probability that an odd number appears when we roll the die? We want an odd number. This is the event that we get 1, 3, or 5. But note in this case they don't have equal probabilities. The probability of 1 is the same as the probability of 2, same as the probability of 4 and 5 and 6. All numbers except 3 have equal probability. It's equal to 1/7. The probability now of 3 is twice as that, so it will be 2/7. Now the probability of E is the sum of the probabilities. That's equal to the probability of 1 plus the probability of 3 plus the probability of 5. This is 1/7 plus the probability of 3, which is 2 over 7, plus 1 over 7. This is equal to 4 over 7. Next, we would like to consider probabilities of complements. We already have a relationship, of course, between the probability of an event and its complement. The rule is that the probability of the complement is equal to 1 minus the probability of the event. This still holds. Now, if you think of any outcome in the sample space is either an E or it should be in its complement. And if you take the union of E and its complement, you get the entire sample space. Now the probability of the sample space is equal to 1, or the sum of the probabilities is equal to 1. That's equal to the probability of E plus the probability of its complement. Of course, this is consistent with the previous formula, that the probability of the complement is equal to 1 minus the probability of the event. We also considered, in the case where two events are not disjoint, that the probability of the union, probability of E1 union E2, is equal to the probability of E plus the probability of E2 minus the probability of the intersection. For the case of E and its complement, these are disjoint. The probability of the complement is 0. We get the same formula. Now, you can generalize this rule for any finite number of events. So if E1, E2, any finite number of events, the case where they are pairwise disjoint, معناتها I know two events have something in common, then the general formula that the probability of the union of the events would be the sum of the probabilities. The condition they have to be pairwise disjoint events. Next, we would like to study conditional probability, and starting with the definition, let E and F be events with the probability of F greater than 0. The conditional probability of E given F, and the way we write it is we write P, E, then a vertical line, F. Here the condition is F. We want to calculate the probability of E occurring given that the condition F has occurred. By definition, the conditional probability of E given F is equal to the probability of E intersected with F divided by the probability of the condition, the probability of F. Using this formula, you can calculate the probability of E given F. Here is an example of conditional probability. We have a bit string of length 4 is generated by a random process so that each of the 16 bit strings of length 4 is equally likely. What is the probability that it contains at least 2 consecutive zeros given that its first bit is 0? The event we are trying to calculate the probability for, that the picking a string at random, we want to know the probability it contains at least 2 consecutive zeros. Now, what is the condition? The condition given that its first bit is equal to 0. Let's start by defining the different events. Here, E is the event that the bit string contains at least 2 consecutive zeros. The condition F is the event that the first bit is 0. What is the intersection? E and F are all those bit strings that have 2 consecutive zeros and start with the digit 0. These are the different bit strings, which is the intersection of E and F. It is the bit string of length 4, that's all zeros, 001, 0010, 0011, 0100. These are all the bit strings that satisfy both conditions. Yani they start with 0 and they have at least two consecutive zeros. Now, what is the probability of the intersection? Well, there is 1, 2, 3, 4, 5 bit strings in the intersection, divided by the total number of bit strings. That will be 5 divided by 16. Now, how many bit strings? And we want also to know the probability of the condition. Condition in the bit strings start with 0, where the probability of f can be calculated. You have, out of the 8 bit strings we have that have length 4, actually we have 16 bit strings altogether, but 8 of them start with 0 and the other 8 start with 1. The probability of f, the probability of bit strings that start with 0 is 8 divided by 16, which is equal to 1/2. Now we are ready to calculate the probability. The probability of E given f, again this is the probability of obtaining a bit strings that have two consecutive zeros given a condition given in the bit string start with 0. But this is the probability of the intersection, which we calculated to be 5 divided by 16, divided by the probability of the condition, which is 1/2. That's equal to 5/8. Here's another example of conditional probability. We want to calculate the probability, the conditional probability, that a family with 2 children has 2 boys, given that they have at least 1 boy. And we want to assume that we have equal probabilities. The 4 possible outcomes is that the family has, BB means you have a boy in the first child. First child is a boy, the second child is a boy. Boy girl means the first child is a boy, the second child is a girl. Or GB, and the final outcome is GG. These are all equally likely events. The 4 possible outcomes are all equally likely. Let's start by defining our event. E is the event that the family has 2 boys. F is the event that the family has at least 1 boy. We want to calculate the probability of E given F. E, of course, the event that the family has 2 boys, there's only 1 outcome, which is BB. The event that the family has at least 1 boy has 3 outcomes, BB, BG, or GB. Their intersection would be the intersection of E and F is just the outcome BB. Now the probability of F, there is 3 outcomes in F, but the probability of F is 3/4. The probability of the intersection, there's only 1 outcome, so it's equal to 1/4. Now the conditional probability of E given F, the probability that the family has 2 boys, given that they have at least 1 boy, is the probability of the intersection, which we calculated to be 1/4, divided by the probability of F, which we calculated to be 3/4, and the final result should be 1/3. Next, we'd like to look at another concept in probability, is the idea of independence. The definition, 2 events, E and F, are called independent if and only if the probability of the intersection, probability of E intersected with F, is equal to the product of the probability, which is the probability of E times the probability of F. Of course, if 2 events are not independent, and if they don't satisfy this condition, we will say that they are dependent. Here is an example. Let A be the event that a randomly generated bit string of length 4 begins with 1. F is the event that this bit string contains an even number of 1s. and we want to see whether E and F are independent. If the 16-bit strings of length 4 are equally likely. طبعا your sample space, there's 16-bit strings of length 4, and we want to see that the events that we defined are independent or dependent. Now, how many bit strings start with 1? Well, there's 8 bit strings that start with 1. So the event E has 8 strings. Now, what about the F, the outcome, the event F? There's 8 bit strings that contains an even number of ones. Because the number of bit strings of length 4, there's 16. Half of them will have an even number of ones, and half of them will have an odd number of ones. So the two events have the same number of elements. Their probability will be equal. The probability of E is equal to the probability of F, which is 8 over 16, which is equal to 1/2. Now, what about the intersections? The intersection would be those bit strings that start with 1 and have an even number of ones. They are listed. There is 4 of them. The probability of the intersection is 4 over 16, which is 1/4. Now let's check the condition for independence. The probability of the intersection is 1/4. This is the same as 1/2 times 1/2, which is equal to the probability of E times the probability of F. Then the two events are independent. Let's look at another example. Assume, like in the previous example, that each of the 4 ways a family can have 2 children, which is the 4 outcomes BB, GG, BG, and GB. Supposing each outcome is equally likely, let's look at an event. E is the event that the family with 2 children have 2 boys, and F is the event that the family with 2 children has at least 1 boy. Are they independent? Well, let's check. We already calculated some of those probabilities. The probability of the event of having 2 boys is only one outcome, which is BB, but the probability of E is equal to 1/4. The probability of having at least 1 boy, there's 3 outcomes, but the probability will be 3 divided by 4. What about the intersection? The intersection has only 1 outcome, which is BB. The probability of the intersection is 1/4. Now we can check to see whether E and F are independent. If you multiply the probability of E times the probability of F, this will be 3 over 4 times 1/4, which is 3 over 16. That does not equal 1/4, which is the probability of the intersection. The product of the probabilities of E and F does not equal to the probability of their intersection. So the two events are not independent, they are dependent. Here is one more example. We have a small town that has 1 fire engine and 1 ambulance available for emergencies. The probability that the fire engine is available when needed is 0.98. The probability that the ambulance is available when called is 0.92. In the event of an injury resulting from a burning building, and you need both the ambulance and the fire engine, we want to know the probability that both the ambulance and the fire engine will be available. Here we will assume that they operate independently. Here we will use that fact to calculate the probability of the intersection. We will first let A be the event that the fire engine is available, and B is the event that the ambulance is available. We want to know the probability of A and B, that both are available. Since we know that they are independent, and the probability of the intersection is equal to the probability, the product of the two probabilities, This is equal to 0.98 times 0.92, which is equal to 0.9016. Next, we would want to look at different types of distributions. We will first look at what we call Bernoulli trials. These are conditions, and using these conditions we'll define a probability distribution. What is a Bernoulli trial? It is an experiment that can have only two possible outcomes. For example, flipping the coin, there is two outcomes, either tail or head. The other example that we looked at is the random generation of a bit. The bit could be either 0 or 1. The experiment can have only two possible outcomes. Each performance of the experiment is called a Bernoulli trial. An outcome is called a success. One of the outcomes is called a success, and the other one is a failure. The third condition, if P is the probability of success, Q is the probability of failure, the sum must equal to 1. Many problems, one of the distribution we'll look at, actually counts the number of successes when a Bernoulli experiment is repeated so many times. And when you have n mutually independent Bernoulli trials, you count the number of successes in n trials, that will give you a distribution, which we will consider. Again, there's only two outcomes. To have a Bernoulli trial, there should only be two outcomes for the experiment. One we will call a success, and the other one we will call failure. The probability of failure plus the probability of success must equal to 1. We will look at a distribution which is basically counting the number of successes in n independent Bernoulli trials. Let's look at an example of Bernoulli trial. A coin is biased so that the probability of heads is 2/3. That means the probability of tail is 1/3. We want to know the probability that exactly 4 heads occur when the coin is flipped 7 times. First of all, why is this a Bernoulli trial? When you flip a coin, you either get a head or tail. In this problem, we are interested in number of heads, so here we will consider that getting a head is success. That means getting a tail is a failure. The probability of heads, or the probability of success, is 2/3. The probability of failure will be 1/3. Failure here is getting a tail. We want to know the probability of getting exactly 4 heads in 7 trials. We want to get the number. If we repeat this experiment 7 times, we want to know the probability of getting exactly 4 heads or 4 successes. The first thing, how many possible outcomes? You are repeating the experiment, or you're tossing the coin 7 times. Each time there is 2 outcomes, either success or failure, either heads or tail. The number of possible outcomes is 2 times itself 7 times, or 2 to the 7, or 128 possible outcomes. The number of ways 4 of these 7 flips can be heads is 7 choose 4. You have 7 different trials. To get exactly 4 successes, the number of ways you can do this is 7 choose 4. The probability of each of the outcomes, the number of ways you can have exactly 4 successes is equal to 7 choose 4. The probability of each of those outcomes, now remember you have exactly 4 successes, So you multiply 2 over 3 by itself 4 times, and you have 3 failures, so you multiply 1 over 3 by itself 3 times. That is the probability of each of the outcomes, where you get exactly 4 successes. Now, the 7 flips are independent. The probability that exactly 4 heads occur, you can طبعا أول شيء counting the number of ways you can get exactly 4 heads times the probability of each of these outcomes, which is 2 over 3 to the power 4 times 1 over 3 to the power 3. This probability will be 560 divided by 2187. This actually give rise to a new distribution. We'll call it the binomial distribution, but this is basically assigning a probability, the probability of exactly k successes in n independent Bernoulli trials, with the probability of success equal p. The probability of failure, which is q, is equal to 1 minus p. There is a formula where you can calculate that probability. It is n choose k times p to the k times q to the n minus k. فإذا you take n choose k, but then the probability of success raised to power k times the probability of failure raised to the power n minus k. This is طبعا we'll give it a name. This is a binomial distribution. There is 3 parameters that for each experiment, a binomial experiment. K, the number of successes we're interested in. N, the number of times that the experiment is repeated. And P is the probability of success. And this is the formula now to calculate the probability. We use طبعا B stands for the binomial, and the 3 parameters K and P. K again is the number of successes we're interested in. N is the number of times the experiment is repeated. P is the probability of success. This is equal to N choose K, P to the power K times Q to the power N minus K.